Objective 2. The student will be able to give and apply the definition of a function. The previous graph and the graph that we had in Objective 1 was the graph of y equals x squared plus 2, I believe. That graph is the graph of a function. The idea of a function is this. It's a correspondence. Okay, a function is not a set, as is sometimes claimed. It's a correspondence or a rule. A function is a correspondence between two sets, D and R. Now we're talking about sets, D and R. Correspondence between two sets D and R such that to each element of the first set D there corresponds one and only one element of the second set R. The words one and only one are the most important words of this definition, and another way to say one and only one is to say exactly one. In other words, for functions, for every input, there's exactly one output. And so if you remember that, which is easy to remember, you'll do well. For every input, there's exactly one output if you have a function. The first set, the D, the first set is called a domain. So the domain is a set. So if you're ever asked for a domain, and you will be, make it clear that you understand that you're talking about a set. For example, just an inequality would be inappropriate. An inequality is not a set nor an element of a set. The first set is called the domain, and the set of corresponding elements in the second set is called the range. For example, you could have a pizza function. Cost of a pizza C is related to the size of the pizza. A 10-inch diameter pizza costs $9, while a 16-inch diameter pizza costs $12. So C could be 9 or 12, and it's a function of the size of the pizza. The domain is the set of x values. The range is the set of y values. Now when we say that the domain is the set of x values, what we're really saying is that the domain is the set of x values which are allowed. What does that mean? It means allowed. They have to be allowed or permitted. Well, what isn't allowed? What is not allowed to be? Well, 0 in a denominator is not allowed. Negative under an even root. You can't have a negative under a square root, for example. That's not allowed. Any x value which does one of these things is not allowed. And so here's our pizza function as a map. You can visualize a function by the following diagram, which shows a correspondence between two sets, D and R. D is the domain of the function, and that's the size of the pizza, and it gives the each domain element is mapped to a range element. R is the range of the function, and those are costs of the pizza. So you can see how the mapping goes. 10-inch diameter pizza, $9. 12-inch diameter pizza, $10. 16-inch diameter pizza would be $12. And there's a mapping that takes place. And for every size of a pizza, there's exactly one cost of a pizza. If in an equation in two variables we get exactly one output, value of the dependent variable, for each input, value of the independent variable. In other words, if in an equation in two variables we get exactly one y value for each x value, then the equation specifies a function. The graph of such a function is just the graph of the specifying equation, the set of ordered pairs that make the equation true. If we get more than one output for a given input, the equation does not specify a function. So, stated negatively, if we get more than one output for a given input, the equation does not specify a function. Here's an equation. Do we have a function here? Well, do we have a function here? What happens when you run an input through the old function machine? Well, let's just take any x value we like. How about -2? We will throw it into the old function machine. What is this function machine? This is the square the input and subtract 2 machine. That's what that function does. It squares the input and subtracts 2. So the input is -2. It's going to get squared and the result subtracted from by 2. So it's going to be 4 minus 2, or 2. So when you put a -2 into the machine, you get a 2 out of the machine. In other words, when x is -2, y is 2. And the ordered pair, -2, 2, is an ordered pair of the function. Well, let's see. Here's a picture of a curve in the xy plane. And do we have a function here? Well, if you think about it, you got an x value, and for every x value there's only supposed to be one y value, but here's an x value which looks like a little bit less than 3, for which there are 2 different y values. And so that's not going to be the graph of a function. And to say that there's an x value for which there are 2 different y values corresponding to 2 different y values is to say that you can draw a vertical line which intersects the curve twice. You can draw a vertical line. It only takes one. It only takes one. It doesn't matter that you could draw a vertical line which intersects one. Well, you could if you had better artwork than I did that time. But it doesn't matter that you can do that if you can draw a vertical line that has only one point of intersection, or that has 2 points of intersection with the graph. If it's possible to do that, then the graph is not the graph of a function. What about the bottom one? Is that the graph of a function? Yes, it is, because no matter where you would draw a vertical line, it's only going to intersect that graph in one place. So it passes this test, and it is the graph of a function. Any vertical line crosses only once. So vertical line test is what we just did. If you have a graph of an equation, there's an easy way to determine whether it would be the graph of a function. It is called the vertical line test. So here's a statement of it, of the VLT. An equation specifies a function if each vertical line in the coordinate system passes through at most, that means no more than one time, at most one point on the graph of the equation. There's also a negative way to state the definition of the vertical line test. Okay, so this is really all we need to know. That is the VLT right there. But it's good to understand also the negative way to state the VLT. If any vertical line passes through two or more points on the graph of an equation, the equation does not specify a function. Function notation. The following notation is used to describe function. The variable y will now be called f of x. So we want to remember always that y equals f of x. Y always equals f of x. Whenever you see an f of x in this course, you're talking about a y. This is read as f of x, right? It's not f times x, just because you have two things next to each other. The notation means f of x, and it is the y coordinate of the function corresponding to a given x value. So previous equation was y equals x squared minus 2. It can now be expressed as f of x equals x squared minus 2. So it's the same thing, we just wrote f of x instead of y. You know, in a calculator, we've got y1, y2, y3, but we sometimes find it helpful to refer to those three functions as f, g, and h, just as we would, you know, do better to call three students Frank, Gary, and Harry instead of student 1, student 2, and student 3. Evaluating a function. Sometimes that's the problem that you get in your homework. Evaluate a function. So here's the same function, x squared minus 2. What does f of negative 3 equal? So, of course, that's the x, right? Negative 3 is the x. That's going to get thrown into the old function machine. Then there's going to be an output, and that's what f of negative 3 equals. So we replace x with the value negative 3. Negative 3 goes into here for x, and it's going to replace x wherever we see x. So it's going to get squared, the result subtracted from, by 2. Now, here the sign is messed up, and again it says plus, and I'm wondering whether this really means minus or whether the original function was really a plus. But apparently it's really a plus because the output is 11. So this was plus the whole time. F of negative 3 is 11. Okay, so here we have an f of x equals y. F of x equals y. When x is negative 3, y is 11. And that means the point xy, negative 3, 11, is on the graph of the function. Very important point right there. Don't lose that. F of negative 3 equals 11 means that the point negative 3, 11 is on the graph of the function. Some examples. Okay, here's a function, square root of the difference of 3x and 2. Well, what is f of 2? Well, plug it in. Multiply the 2 by 3, you have 6. Subtract 2, you have 4, the square root of which are 2. So the answer is 2. F of 2 equals 2. What is f of a? Well, f of a is just the same thing as f of x, except you're going to replace the letter x with the letter a. We really could have used any letter anyway. So it's just going to be square root of 3a minus 2. What is f of 6 plus h? F of 6 plus h. Well, remember that f of anything is square root of 3 times that thing minus 2. Well, now that thing is 6 plus h. So inside these parentheses we're going to have 6 plus h. And that's going to get tripled, which is 18 plus 3h. The result subtracted from by 2, the result square rooted. Of course, we could combine the 18, that's constant, as is the negative 2. So these two things can be combined. That's going to be 16. Of course, the 3h is not like with the other two things. It cannot be combined. We're going to have the 16 and the 3h. That is not 19h. So we are not going to simplify that, or as it were. It's not the square root of 19h, it's just the square root of 16 plus 3h.